In programming language theory and proof theory, the Curry-Howard correspondence is the direct relationship between computer programs and mathematical proofs. It is a generalization of a syntactic analogy between systems of formal logic and computational calculi that was first discovered by the American mathematician Haskell Curry and logician William Alvin Howard. It is the link between logic and computation that is usually attributed to Curry and Howard, although the idea is related to the operational interpretation of intuitionistic logic given in various formulations by L. E. J. Brouwer, Arend Hating and Andrei Kolmogorov and Stephen Klein. The relationship has been extended to include category theory as the three-way Curry-Howard-Lambert correspondence: origin, scope, and consequences. At the very beginning, the Curry-Howard correspondence is the observation in 1934 by Curry that the types of the combinators could be seen as axiom schemes for intuitionistic implicational logic. The observation in 1958 by Curry that a certain kind of proof system, referred to as Hilbert-style deduction systems, coincides on some fragment to the typed fragment of a standard model of computation known as combinatory logic. The observation in 1969 by Howard that another, more high-level proof system, referred to as natural deduction, can be directly interpreted in its intuitionistic version as a typed variant of the model of computation known as lambda calculus. In other words, the Curry-Howard correspondence is the observation that two families of formalisms that had seemed unrelated, namely, the proof systems on one hand, and the models of computation on the other, were, in the two examples considered by Curry and Howard, in fact structurally the same kind of objects. If one now abstracts on the peculiarities of this or that formalism, the immediate generalization is the following claim: a proof is a program, the formula it proves is a type for the program. More informally, this can be seen as an analogy that states that the return type of a function is analogous to a logical theorem, subject to hypotheses corresponding to the types of the argument values passed to the function, and that the program to compute that function is analogous to a proof of that theorem. This sets a form of logic programming on a rigorous foundation. Proofs can be represented as programs, and especially as lambda terms, or proofs can be run. The correspondence has been the starting point of a large spectrum of new research after its discovery, leading in particular to a new class of formal systems designed to act both as a proof system and as a typed functional programming language. This includes Martin Loeff's intuitionistic type theory and Cochran's calculus of constructions, two calculi in which proofs are regular objects of the discourse and in which one can state properties of proofs the same way as of any program. This field of research is usually referred to as modern type theory. Such types lambda calculi derived from the Curry-Howard paradigm led to software like Coq in which proofs seen as programs can be formalized, checked, and run. A converse direction is to use a program to extract a proof, given its correctness, an area of research closely related to proof-carrying code. This is only feasible if the programming language the program is written for is very richly typed. The development of such type systems has been partly motivated by the wish to make the Curry-Howard correspondence practically relevant. The Curry-Howard correspondence also raised new questions regarding the computational content of proof concepts that were not covered by the original works of Curry and Howard. In particular, classical logic has been shown to correspond to the ability to manipulate the continuation of programs and the symmetry of sequent calculus to express the duality between the two evaluation strategies known as call by name and call by value. Speculatively, the Curry-Howard correspondence might be expected to lead to a substantial unification between mathematical logic and foundational computer science. Hilbert-style logic and natural deduction are but two kinds of proof systems among a large family of formalisms. Alternative syntaxes include sequent calculus, proof nets, calculus of structures, etc. If one admits the Curry-Howard correspondence as the general principle that any proof system hides a model of computation, a theory of the underlying untyped computational structure of these kinds of proof systems should be possible. Then, a natural question is whether something mathematically interesting can be said about these underlying computational calculi. Conversely, combinatory logic and simply typed lambda calculus are not the only models of computation, either. Girard's linear logic was developed from the fine analysis of the use of resources in some models of lambda calculus. Can we imagine a typed version of Turing's machine that would behave as a proof system? Typed assembly languages are such an instance of low-level models of computation that carry types. Because of the possibility of writing non-terminating programs, Turing-complete models of computation must be interpreted with care, as naive application of the correspondence leads to an inconsistent logic. The best way of dealing with arbitrary computation from a logical point of view is still an actively debated research question. But one popular approach is based on using monads to segregate provably terminating from potentially non-terminating code. A more radical approach, advocated by total functional programming, is to eliminate unrestricted recursion, using more controlled co-recursion wherever non-terminating behavior is actually desired. General formulation. In its more general formulation, the Curry-Howard correspondence is a correspondence between formal proof calculi and type systems for models of computation. In particular, it splits into two correspondences. One at the level of formulas and types, that is independent of which particular proof system or model of computation is considered, and one at the level of proofs and programs, which, this time, is specific to the particular choice of proof system and model of computation considered. At the level of formulas and types, the correspondence says that implication behaves the same as a function type, conjunction as a product type, disjunction as a sum type, the false formula as the empty type and the true formula as the singleton type. Quantifiers correspond to dependent function space or products. This is summarized in the following table. At the level of proof systems and models of computations, the correspondence mainly shows the identity of structure, first, between some particular formulations of systems known as Hilbert-style deduction system and combinatory logic, and, secondly, between some particular formulations of systems known as natural deduction and lambda calculus. Between the natural deduction system and the lambda calculus there are the following correspondences. Corresponding systems. Hilbert-style deduction systems and combinatory logic. It was at the beginning a simple remark in Curry and Fice's 1958 book on combinatory logic. The simplest types for the basic combinators K and S of combinatory logic surprisingly corresponded to the respective axiom schemes alpha and used in Hilbert-style deduction systems. For this reason, these schemes are now often called axioms K and S. Examples of programs seen as proofs in a Hilbert-style logic are given below. If one restricts to the implicational intuitionistic fragment, a simple way to formalize logic in Hilbert's style is as follows. Let gamma be a finite collection of formulas, considered as hypotheses. We say that delta is derivable from gamma, and we write gamma delta, in the following cases. Delta is an hypothesis, i.e., it is a formula of gamma. Delta is an instance of an axiom scheme, i.e., under the most common axiom system. Delta has the form alpha, or delta has the form delta follows by deduction, i.e., for some alpha, both alpha delta and alpha are already derivable from gamma. This can be formalized using inference rules, what we do in the left column of the following table. We can formulate typed combinatory logic using a similar syntax. Let gamma be a finite collection of variables, annotated with their types. A term t will depend on these variables, gamma t, delta, when t is one of the variables in gamma. T is a basic combinator, i.e., under the most common combinator basis. T is K, alpha, where alpha and beta denote the types of its arguments, or T is S smiley face. T is the composition of two subterms which depend on the variables in gamma. The generation rules defined here are given in the right column below. Curry's remark simply states that both columns are in one-to-one correspondence. The restriction of the correspondence to intuitionistic logic means that some classical tautologies, such as Peirce's law alpha, are excluded from the correspondence. Seen at more abstract level, the correspondence can be restated as shown in the following table. Especially, the deduction theorem specific to Hilbert-style logic matches the process of abstraction elimination of combinatory logic. Thanks to the correspondence, results from combinatory logic can be transferred to Hilbert-style logic and vice versa. For instance, the notion of reduction of terms in combinatory logic can be transferred to Hilbert-style logic, and it provides a way to canonically transform proofs into other proofs of the same statement. One can also transfer the notion of normal terms to a notion of normal proofs, expressing that the hypotheses of the axioms never need to be all detached. Conversely, the non-provability in intuitionistic logic of Peirce's law can be transferred back to combinatory logic. There is no typed term of combinatory logic that is typable with type alpha. Alpha results on the completeness of some sets of combinators or axioms can also be transferred. For instance, the fact that the combinator X constitutes a one-point basis of combinatory logic implies that the single axiom scheme zeta, which is the principal type of X, is an adequate replacement of the combination of the axiom schemes alpha and natural deduction and lambda calculus. After Curry emphasized the syntactic correspondence between Hilbert-style deduction and combinatory logic, Howard made explicit in 1969 a syntactic analogy between the programs of simply typed lambda calculus and the proofs of natural deduction. Below, the left-hand side formalizes intuitionistic implicational natural deduction as a calculus of sequence with implicit weakening, and the right-hand side shows the typing rules of lambda calculus. In the left-hand side, gamma 1 and gamma 2 denote ordered sequences of formulas, while in the right-hand side, they denote sequences of named formulas with all names different. To paraphrase the correspondence, proving gamma alpha means having a program that, given values with the types listed in gamma, manufactures an object of type alpha. An axiom corresponds to the introduction of a new variable with a new, unconstrained type. The I rule corresponds to function abstraction and the E rule corresponds to function application. Observe that the correspondence is not exact if the context gamma is taken to be a set of formulas as, e.g., the lambda terms lambda x, lambda y, x and lambda x, lambda y, y of type alpha would not be distinguished in the correspondence. Examples are given below. Howard showed that the correspondence extends to other connectives of the logic and other constructions of simply typed lambda calculus. Seen at an abstract level, the correspondence can then be summarized as shown in the following table. Especially, it also shows that the notion of normal forms in lambda calculus matches Pravitz's notion of normal deduction in natural deduction, from what we deduce, among others, that the algorithms for the type and habitation problem can be turned into algorithms for deciding intuitionistic provability. Howard's correspondence naturally extends to other extensions of natural deduction and simply typed lambda calculus. Here is a non-exhaustive list. Girard-Reynolds system F is a common language for both second-order propositional logic and polymorphic lambda calculus. Higher-order logic and Girard's system F omega. Inductive types as algebraic data type. Necessity in modal logic and staged computation. Possibility in modal logic and monadic types for effects. The lambda I calculus corresponds to relevant logic. the local truth modality in graph-ND topology, or the equivalent LAX modality of Benton, Biermann, and Apida correspond to CL logic describing computation types, classical logic and control operators at the time of Curry, and also at the time of Howard. The proofs as programs correspondence concerned only intuitionistic logic, i.e., a logic in which, in particular, Peirce's law was not deducible. The extension of the correspondence to Peirce's law and hence to classical logic became clear from the work of Griffin on typing operators that capture the evaluation context of a given program execution so that this evaluation context can be later on reinstalled. The basic Curry-Howard style correspondence for classical logic is given below. Note the correspondence between the double negation translation used to map classical proofs to intuitionistic logic and the continuation passing style translation used to map lambda terms involving control to pure lambda terms. More particularly, call by name continuation passing style translations relates to Kolmogorov's double negation translation, and call by value continuation passing style translations relates to a kind of double negation translation due to Kuroda. A finer Curry-Howard correspondence exists for classical logic if one defines classical logic not by adding an axiom such as Peirce's law, but by allowing several conclusions in sequence. In the case of classical natural deduction, there exists a proofs as programs correspondence with the typed programs of Paragat's lambda mu calculus. Sequent calculus. A proofs as programs correspondence can be settled for the formalism known as Jensen's sequent calculus, but it is not a correspondence with a well-defined pre-existing model of computation as it was for Hilbert style and natural deductions. Sequent calculus is characterized by the presence of left introduction rules, right introduction rule and a cut rule that can be eliminated. The structure of sequent calculus relates to a calculus whose structure is close to the one of some abstract machines. The informal correspondence is as follows. Related proofs as programs correspondences. The role of De Bruijn N. G. De Bruijn used the lambda notation for representing proofs of the theorem checker or to math, and represented propositions as categories of their proofs. It was in the late 1960s, at the same period of time Howard wrote his manuscript. De Bruijn was likely unaware of Howard's work, and stated the correspondence independently. Some researchers tend to use the term Curry-Howard-De Bruijn correspondence in place of Curry-Howard correspondence. Bhk interpretation. The Bhk interpretation interprets intuitionistic proofs as functions, but it does not specify the class of functions relevant for the interpretation. If one takes lambda calculus for this class of function, then the Bhk interpretation tells the same as Howard's correspondence between natural deduction and lambda calculus. Realizability. Cleans recursive realizability splits proofs of intuitionistic arithmetic into the pair of a recursive function and of a proof of a formula expressing that the recursive function realizes, i.e., correctly instantiates the disjunctions and existential quantifiers of the initial formula so that the formula gets true. Krasel's modified realizability applies to intuitionistic higher-order predicate logic and shows that the simply typed lambda term inductively extracted from the proof realizes the initial formula. In the case of propositional logic, it coincides with Howard's statement. The extracted lambda term is the proof itself, and the realizability statement is a paraphrase of the fact that the extracted lambda term has the type that the formula means. Gödel's dialectica interpretation realizes intuitionistic arithmetic with computable functions. The connection with lambda calculus is unclear, even in the case of natural deduction. Curry-Howard-Lambert correspondence. Joachim Lambert showed in the early 1970s that the proofs of intuitionistic propositional logic and the combinators of typed combinatory logic share a common equational theory, which is the one of Cartesian closed categories. The expression Curry-Howard-Lambert correspondence is now used by some people to refer to the three-way isomorphism between intuitionistic logic, types lambda calculus and Cartesian closed categories, with objects being interpreted as types or propositions and morphisms as terms or proofs. The correspondence works at the equational level and is not the expression of a syntactic identity of structures as it is the case for each of Curry's and Howard's correspondences, i.e., the structure of a well-defined morphism in a Cartesian closed category is not comparable to the structure of a proof of the corresponding judgment, in either Hilbert-style logic or natural deduction. To clarify this distinction, the underlying syntactic structure of Cartesian closed categories is rephrased below. Objects are defined by as an object, if and are objects then and are objects. Morphisms are defined by and are morphisms, if is a morphism, if and are morphisms, and are morphisms. Well-defined morphisms are defined by the following typing rules: identity, composition, unit type, Cartesian product, left and right projection, currying, application. Finally, the equations of the category are. Now, there exists such that IFF is provable in implicational intuitionistic logic.